Hi, today we are going to study simple harmonic motion. So firstly let me explain you what motion is. Okay. Say for example I have a ball. Okay. So I am going to take this position, let it be at position x1 at time equal to 0. Then I will push this ball, it moves. So at time equal to some 5 seconds it would have moved and its position will be x2. Then again at time equal to some 10 seconds it would have moved further, so its position is going to be x3. So what is happening here? The position of the body is changing with time. Then we say that the body is in motion. So a body is in motion if its position changes with time. Okay. So now we understand what is motion. So rest means what? Its position does not change, so it is going to be at rest. So now motion can be of periodic. Some motions are periodic. Okay. So what do you mean by periodic? Some motions are actually periodic. So whenever I use the word periodic means something which repeats. Okay, something repeats. Okay, something which repeats. Okay, so now I am going to say motion is periodic means that motion is getting repeated. Say for example I am going to take a thread and I am going to tie a stone at the end of the thread and I am going to hold it like this and I am going to rotate it. Then what happens? Okay, the stone will start moving in a circular motion. So it is moving in this motion like this, it is moving. Okay, so this circular orbiting of this stone is getting repeated again and again. So this sort of motion is called as periodic motion. So another kind of periodic motion is oscillation. So now say for example something is oscillating. Okay, now you take a swing, so you have a swing, a person is sitting, so they are going to move like this, right and then again to left. So this swing person, the kid on the swing is moving right and left, so they are oscillating. So this swing is moving to and fro, or it is executing, the swing is executing to and fro motion. So this sort of oscillatory motion or to and fro motion is also periodic. Okay, so now before getting too deep into this sort of oscillatory motion, let us understand what is equilibrium position or mean position. Okay, for this I am going to take a pendulum or as an example. Okay, so you have a pendulum here. Okay, now this pendulum is at rest. So that is rest means it is not in motion, no force is acting on that. So what happens now here? This position of the pendulum is called as mean position or equilibrium position. Or equilibrium position. So it is the position of the pendulum when it is at rest. So now what I will do, I am going to move this pendulum in this form. I am just going to move it and I am going to release it. Then what happens? This pendulum starts oscillating. Okay, it goes to the left and then it passes the mean position, goes to the right, again comes back to the mean position and then goes to the right. So it's going to oscillate. So this is nothing but simple periodic motion. Okay, it is a simple harmonic motion or periodic motion, you can actually call it. So what is happening here? A body is oscillating or executing to and fro motion about a mean position. Okay, so this is the basic definition, simple definition. We are not going too technical in it. Okay, now let us see little bit, go deeper. What happens now when you actually the bob is in this direction, or the pendulum is at this point, let me say x1 position. When it is at x1 position, what happens? So there is some restoring force. Okay, there is a force which tries to pull it back to the mean position. Okay, so it tries to restore the bob back to the mean position, that is equilibrium position. So there is a restoring force. So what is happening? There is a restoring force. Okay, there is a restoring force which tries to bring back the body to the mean position or equilibrium position, to the mean or equilibrium position. Okay, okay, so let me represent this restoring force by the symbol F. So F is going to be the restoring force. Okay, so now I would like to say two things about this restoring force. Now this restoring force, what happens? It is directly proportional to the displacement. Now if the pendulum is here, it is going to have F1 restoring force. If the pendulum is here in this x2 position, it is going to have F2 restoring force. If the pendulum is in x1 position, there is going to be F1 restoring force. So F1 is greater than F2. Okay, that means what? This restoring force, this F restoring force is directly proportional to the displacement. So displacement is nothing but x2 and x1. So how much it has got displaced from the equilibrium position? So this x is going to be the displacement from the mean position. Okay, so more the displacement, more will be the force. So if the bob is near the mean position, then the restoring force will be less. If the bob has moved far away from the restoring mean position, then the restoring force is going to be more. So this restoring force is directly proportional to the displacement. Now what about the direction of this restoring force? Now this restoring force is negative to the displacement. Okay, there is going to be a minus sign. So what is happening here? So the force is in this direction. Okay, but the displacement is in this direction. The bob is moving like this. Okay, you have this equilibrium position. The bob is moving like this. So your x is like this. Okay, but your restoring force is like this. So your restoring force is negative of the displacement. Okay, so now what is happening? I have a proportionality constant. I am going to make it to equal, that is going to be kx. K is going to be what? A proportionality constant. Okay, it's a proportionality constant. Okay, so this is about the SHM. Okay, now we will try to get the equation representing this SHM. So now we know that force equal to, okay, fifth point, force equal to mass into acceleration. Okay, okay, so F equivalent to mass into acceleration. We know that it is a second derivative of position with respect to time, isn't it? So now I have fourth equation and fifth equation. So equate 4 and 5. So when you equate both of them, so what will you get? You're going to get m second derivative of x with respect to t is going to be minus kx. Okay, so now what I'm going to do, just simple adjustment, that's all. So I'm going to put del square x by x m plus kx equal to 0. Then I'm going to divide everything by mass. So I'm going to get k by m x equal to 0. Now I'm going to put this both are constant. K is constant, mass is also going to be constant. The mass of the pendulum is not going to change. So this is a constant. So I'm going to say put omega square equivalent to k by m. So then what will I get? I'm going to get d square x by dt square plus omega square x equivalent to 0. So this is going to be the differential equation for the SHM. So this equation is nothing but it is the differential equation for simple harmonic motion. Simple harmonic motion. Okay, so these are the basics of simple harmonic motion. Okay, thank you.